access to YouTube. Right now. Okay, we did it. We're live.
Yeah.
I think. I can't. I need, as always, the joke I make is I require like some external confirmation of our existence. Someone to
Confirmation.
collapse the wavefront and the wave function and tell us that we actually exist. But
Right.
I'm sure it's working. But I hope we've been having a couple of audio issues for the last couple of episodes, and I think I've sorted them out. So hopefully, when you introduce yourself, your audio is going to work well, and your people are going to be hear you just great. So let me give it a try. So why don't you introduce yourself? Who are you? What do you do?
I am Nikku Madhusudhan. I am a professor of astrophysics and exoplanetary science at the Institute of Astronomy at Cambridge. So my main area of research is exoplanet atmospheres, but I work in a few different areas within exoplanetary science, connecting their atmospheres, interiors, planet formation, and so on.
So you obviously came to all of our attention in the last month or so with quite an interesting paper that you published with your various co-authors about this entirely new category of Hycean world. So can you talk a little bit about the research and what you're proposing?
Yeah. So the idea of this particular paper actually originated about a year ago, more than a year ago. Last year, we published a paper on the planet K218b, which was originally classified as a mini Neptune sitting in the habitable zone of its host star. So this is slightly over 2.5 times Earth radius, the radius of this planet. And at the time, we demonstrated how, we can go into that in more detail, but we demonstrated how even for a planet that big, which originally one would have thought cannot host any habitable conditions at all, we demonstrated that there is a subset of solutions which allow for habitable conditions, liquid water at the right temperatures and pressures on a surface underneath the hydrogen-rich atmosphere. So that sort of got us into thinking, well, if K218b can allow such conditions, what other planets are out there that could allow for similar conditions? And more than planets, just what macroscopic planetary properties allow us, allow the possibility of liquid water on the surface of the planet underneath the hydrogen-rich atmosphere, and the surface being habitable, in habitable conditions. So that's when we went ahead and did this elaborate exploration of the planetary bulk parameter space and came up with this idea of the Hycean worlds.
Right. So, I mean, when we think of a habitable exoplanet, we're imagining something like Earth. We're imagining some kind of world that is within the habitable zone of its parent star, and obviously for a red dwarf star, it's very small zone. For a sun-like star, maybe it's a much wider zone. You've got a rocky planet. It's got a thick an atmosphere that is providing water on top of it. And so I think we can all conceptualize this idea of a rocky world and a terrestrial planet. So what would a thick, what creates, or what is a thick hydrogen atmosphere? How does that differ? I mean, I guess we have a thick nitrogen atmosphere.
Yeah, so we have a nitrogen atmosphere, but the hydrogen-rich atmospheres are actually not that uncommon. All the giant planets in the solar system have hydrogen-rich atmospheres.
Because they're just made of hydrogen.
Yeah, exactly. So the atmosphere is predominantly hydrogen and helium.
Right.
Neptune has it, Uranus has it. So turns out, hydrogen-rich atmospheres are very common and would be the default kind of atmosphere you expect, unless there is something else that happens after the planet formed. And the reason for that is when the planet is forming in a protoplanetary disk around the star, it primarily creates hydrogen. hydrogen and helium. That's what the nebula is made of for the most part.
Right.
And along with that hydrogen and helium, it accretes some other, solids in the form of ices and so on, which contribute to, the oxygen, carbon, and so on in the atmosphere. But for the most part, hydrogen is all it's got, hydrogen and helium in nebular proportions. But then something else happens for smaller planets is that, they can lose the hydrogen over time, and then the secondary outgassed molecules dominate over the atmosphere, and you're left with secondary atmospheres, carbon dioxide rich atmospheres or nitrogen rich atmospheres, and oxygen comes into play at some other point, so on and so forth. So all the rocky planet atmospheres that you see and that we are so accustomed to are actually secondary atmospheres. If that doesn't happen, if you don't lose that original atmosphere in the first place, in other words, if you had, there are various ways to get there. For example, if you started out with a much thicker atmosphere and you haven't lost all of it yet, right? So if it's a bigger planet and it hasn't lost all of its hydrogen, then you retain it. That's one way. Or you outgas hydrogen as well and make up an atmosphere. So there are any number of ways you can make up an hydrogen-rich atmosphere, and you end up with such planets in which hydrogen, by definition, has a low mean molecular weight, which means the atmosphere is puffier. So for the same mass content, you'll have a puffier atmosphere if you have a hydrogen-rich composition.
And we're all fairly familiar with this idea that, say, Mars lost all of its hydrogen because it doesn't have enough gravity, and the solar wind is sort of blowing away the hydrogen atoms out into space. And a similar process is kind of happening on Earth, but we've got a better protection from the sun to be able to stop that. Something similar happened with Venus. So you've got these forces. You've got the sun is trying to get rid of your hydrogen, but I guess if you have enough gravity, you're able to fight that process. Or if you
can hang on to it.
You can hang on to that hydrogen. And so like if we were, say, if Earth was double the mass that it is today, would it have a much richer amount of hydrogen in its atmosphere than we experience today? And would that mean, what would be the consequence of that? Would we have more oceans or just more hydrogen in the atmosphere?
One has to do such a calculation, and I'm sure some people have done those calculations. You could still lose much of your hydrogen over the many billion years of the evolutionary history of the Earth if you're just 2 times over. But let's say you started much bigger with a much thicker atmosphere and you chipped away at it, and then you could still retain some of that atmosphere if you are slightly bigger than just 2 Earth masses. That said, there is an interesting observation being made in the field right now, is that we are seeing smaller planets, like 2 Earth mass planets with potentially hydrogen-rich envelopes, and there are ideas being floated around on how those could be retained as well. So I wouldn't entirely discard the idea of a hydrogen-rich atmosphere around a 2 Earth mass object, but whether in the specific conditions of Earth around a sun-like star with Earth's history, you could still have that is a different question.
Well, you mentioned that there's maybe some ideas on how they could retain this. So, can I hear your speculations on how one of these planets might be able to hold on to its atmosphere?
People have been arguing for outgassing of hydrogen from the interior of the planet, or like you could have you could start with a water-rich planet, but then you dissociate a lot of that water and then you form hydrogen that way. Or, you started as a bigger planet with more of a hydrogen envelope, but then, as I said earlier, you could remove part of the hydrogen envelope, but what is left today is a small core, a 2 Earth mass core with some hydrogen around it.
Right. And so, if you said there are planets that are that have a thick hydrogen atmosphere, as you said, those are the gas giants. We've got Jupiter. We've got one right over there. So why does this get interesting in terms of habitability?
Yeah. So the problem with the hydrogen-rich atmosphere for habitability is that if you have an atmosphere that is too thick, then what happens is that your pressure and temperature, obviously they increase as you go deeper into the atmosphere. And if you have the atmosphere to be too thick, if there is a surface, it'll be extremely hot. So too hot to be habitable. You can have tens of thousands of bars of pressure, 1,000 Kelvin or higher temperatures, many thousands of kelvins of temperatures, and so on. So you couldn't possibly be habitable. That's the situation with Uranus and Neptune in our own solar system. Right. So they're very cold on the surface. The atmosphere is extremely cold, but below freezing, obviously. But then if you go deep enough, the pressures and the temperatures are extremely high. So before you hit any sort of liquid water surface, it's already too hot and high pressures for that. So you end up into supercritical phases of water and never actually end up with liquid water surface. So that is why people in the past had been arguing for even like these mini Neptunes, and I'll get to like the broader picture of mini Neptunes in a second. But even for planets slightly smaller than Uranus and Neptune, if the radius is too big, people had argued that you would have a hydrogen-rich envelope that is too thick to sustain life in the interior. And that is the key, is that it is not, in this particular study, the statement is not that every planet that is smaller than Neptune and cool enough can host life. Mm-hmm. You cannot make that statement. And the reason for that, I'll get into the broader class now, is that as you may well know, the exoplanet demographics today are basically suggesting that planets between Earth and Neptune size, the sub-Neptune type planets, basically overwhelm the population. Like yes. The majority of the population is just those. Yep. Right? Earth is obviously one Earth radius in radius, and Neptune is 4 Earth radii. In that range is where the majority of planets we have found lie. So big Neptunes.
Yep.
And what that means by a smaller Neptune is that you have these hydrogen-rich envelopes and then an icy sort of mantle, an icy interior, and then a rocky core somewhere inside. Right. So you transition from that to like these rocky worlds or super Earths, which are predominantly rock, like Earth and terrestrial planets, and with some secondary atmospheres possibly, or even a hydrogen-rich atmosphere. Where that transition happens, is still not like 100% clear, but there have been theoretical studies and empirical studies which argued for it to be nominally around 1.6 Earth radius. Okay.
So if we, I guess if we moved Neptune into the inner solar system and we got closer and closer to the sun, and it was able to warm up. And so, as you said, right now you've got the outer atmosphere, the upper cloud tops. It's very, very cold. As it goes down, the pressure and temperature heats up, and suddenly you get beyond liquid water into these weird, exotic, high pressure ices and things like that. But we call Neptune and Uranus ice giants. Like, they have the stuff of ice in them. They have water and other constituents inside of them. And so if you took Neptune and brought it into the inner solar system, would there be this point where it would be a more habitable world?
No.
So it's not the kind of planet you're thinking of.
The reason for that is what I was hinting at, is that this transition point around 1.6 Earth radii that people are, it could be like somewhere around that, between super Earths and mini Neptunes. Above that radius, what you're arguing, roughly around above that radius, what you're arguing is that you have to have like a hydrogen. The mini Neptunes are characterized by having hydrogen-rich envelopes. But it's not that you can have any amount of hydrogen-rich envelope and still be habitable.
Right.
So Neptune has 4 Earth radii, right? Which means it needs anywhere between, depends on the models, but anywhere between around 10% to 20% of its envelope mass in hydrogen. So if you stack that much hydrogen on any sort of interior, your pressure and temperature at the bottom of that hydrogen layer would be way too high for any sort of habitability to happen. which means that radius has to come down significantly before you can allow for just the right amount of hydrogen, which will allow just the right amount of pressure and temperature at the base of it.
Okay. So then,
And that, sorry.
oh
And
no, sorry. That makes sense. So maybe if we took Neptune and broke it up into a bunch of smaller planets, then maybe that might do the trick. So then let's take a look again at this, sort of at your perfect Hycean world. And a lot of the science journalists, we were very confused when we heard this word Hycean world. We're like, whoa, what is that? Is that Greek? What does that mean? But it's like hydrogen ocean, Hycean. Yeah, I see what you did there. So what is like your perfect Hycean world?
so if I may go back one step before
Sure. Yep.
I answer that particular question, remember how I just said you need to be at the right limit of radius. In this particular work, we have established what that radius ought to be. So the maximum radius you can be for a Hycean planet is around 2.6 Earth radii for a 10 Earth mass planet. That upper limit is actually a curve. With smaller mass, that maximum limit decreases. For a 5 Earth mass, it will be around 2.2 or so. So that is an upper limit below which you need to be for the surface conditions to still be habitable. Okay, so that is something we need to keep in mind. We cannot go indefinitely in radius and still have a hydrogen-rich atmosphere and be habitable. So having said that, to your question of what is a perfect Hycean world, as long as it's got the mass and radius below that limit I just spoke about, and temperatures, I would like to keep it balmy. Let's call it around 300 Kelvin equilibrium temperature. That should be a pretty decent planet with a decent chance of habitability, I would say.
And what would it look like as you as you fly down in your spaceship and as you descend down through the layers of the cloud tops? What would you be experiencing? What would it look like?
So there are any number of scenarios. So this, when you go into the theories that we work on, there are any number of scenarios that will fit the description of the macroscopic properties, the mass radii, and temperatures, and so on. But one scenario, it could be that you'd find yourself in a very hazy world, lots of hydrocarbons, lots of haze, basically, and then an ocean, infinite ocean around, and the most likely for most of these planets, the temperatures would not be like Earth-like ocean temperatures. They would be significantly hotter. But hotter for us, but not necessarily for the extremophiles we have on Earth. We know on Earth life survives up to around 400 Kelvin temperatures at like high pressures even. So those conditions are technically habitable, right? So that is what we are most likely to encounter on these worlds, is very hot oceans, steamy, the atmosphere very hazy, but there would be endless oceans by construction.
So the higher atmospheric pressure would be acting a bit like a pressure cooker in the way that you can boil water at a much higher temperature in a pressure cooker because you've got that higher pressure. So you might have, you mentioned, say, those worms that live beside the hot smoker vents can appreciate 130 Celsius. There's bacteria that can handle those kinds of just extreme temperatures. As long as there's liquid water, then they can do their job. And so you would have this water that would, I guess, almost be boiling. Like if you tried to swim in it, it would not be pleasant.
It would not be pleasant, no.
Yeah.
So Yeah, so as far as the pressure is concerned, in this work, what we have done is we wanted to construct a habitable zone, you see. So to get to the inner edge of the habitable zone, you have to assume the most, the extreme conditions of pressures and temperatures and all that that would still allow for habitability. But there is no reason why that has to be the norm. You see what I mean? So, you could have planets out there at normal pressures and lower temperatures. So they all don't have to be at 400 Kelvin temperatures. You could have planets out there
Right.
which would be 350 or 300 Kelvin and room pressure, like 1 atmosphere pressure as well. On the other hand, you could also have the other extreme, which is have 1,000 bar pressure atmospheres and extreme temperatures as well. So there's a wide range here.
Well, and I think I think that was the biggest takeaway that I got in reading the paper, was that with a terrestrial planet like Earth, you've got this very thin Goldilocks zone where the temperatures are not too high, not too cold, so that liquid water can exist on the surface of the world. But these Hycean, is the way you're saying it? Hycean worlds?
Yeah.
Yeah, okay, I
Yeah.
like it. Yeah, Hycean worlds. So these Hycean worlds have much wider habitable zones. So how wide?
Yeah. Very, very wide, in the sense that there are two reasons for why they're extremely wide. I'll tell you how wide in a second, but the motivation is just as important. It's that the inner boundary for an Earth-like planet has always been, obviously the Earth's terrestrial habitable zone was constructed with the Earth in mind, right? So if we want literally an Earth-like planet around various kinds of stars,
Yeah.
we keep the Earth surface conditions, the atmospheric conditions, and all that, and make that habitable zone. So
Right.
that's well motivated by what we know of Earth.
And we may find there's only one in the entire observable universe.
I would hope there would be more, but they're just very hard to observe.
Yeah.
If you want, we'll get to biosignatures later on, but they're extremely hard to detect a biosignature in the atmosphere. But when you get to these sorts of planets, the advantage they have is that there are any number of scenarios which allow you to be somewhat closer to their stars, somewhat hotter, and still have habitable surface conditions. One reason being, you can't lose if you have that much water in the planet. You cannot lose, no matter how high you make the temperature. You cannot lose all of it.
Right.
You have basically an infinite source at the bottom. So you could afford to go to much high temperatures and still be habitable, and the atmosphere could be extremely misty, but that's okay, as long as you have the right conditions. So what that allows you is that it takes the inner habitable zone somewhat closer to their host stars than what you would have on Earth. But that is not what expands. It is still like, an expansion of the habitable zone inward, in that you don't now stay at like 300, close to 300 Kelvin, but you could go all the way up to 400 Kelvin temperatures, right. Equilibrium temperatures, right? So that will get you a little bit of orbital distance inward. But what is more interesting is that the outer habitable zone is basically indefinite for these sorts of planets.
Really?
Is that you could be extremely far from the star and even free floating and still have habitable conditions on the surface.
Now, when you say free floating, like you're talking about a rogue planet that has no star, that is just wandering randomly across the Milky Way.
Exactly.
Wow. And so we're kind of, we've talked a bit about just the hotter version. So talk to me about that colder version. What is that looking like?
Yeah, so the colder version is less talked about usually because they're less amenable to detection and observations because they're so far away from their stars. But in terms of the principle of habitability, they're just as important and increase the volume of the region of habitability much more than the hotter ones. The reason for that is that on the Earth, the outer edge of the habitable zone is around 1.7 AU nominally, but then there are model considerations which can move it slightly closer or farther. But for these planets, and that's for the Earth, it's basically because you condense out all the global warming causing gases from the atmosphere. You can condense out CO2 and obviously water and so on. So it becomes extremely cold very quickly. But for these types of planets, the hydrogen itself provides the warming beyond that. So if you have a thick enough hydrogen atmosphere, even up to 1,000 bar atmospheres are feasible, we have shown in this work, those are what we call as the cold Hycean worlds, is that you could have thick hydrogen atmospheres which can allow for liquid water on the surface without any source, even without the star.
That's incredible.
Right? So just the internal energy, the internal heat from the planet itself is enough to sustain liquid water on the surface.
And how long would it last? Like billions of years?
Yeah, it could last billions of years. Easily. And these sorts of planets, actually, without the hydrogen-rich atmospheres, but for rocky planets, have been studied before. This is not a new idea in and of itself. People, in the last 10 to 20 years, even have studied small planets, very far, like terrestrial rocky type planets, very far from their stars, or even like rogue planets, which can possibly sustain liquid water on their surfaces.
Right.
But no one had studied hydrogen rich atmosphere, like these Hycean type of planets with ocean worlds with hydrogen rich atmospheres being far away from their stars or free floating. But we show in this work that that is indeed a possibility, and you can have lots of them out there.
Yeah. So then let's talk about this definition of habitability, because we know, of course, the classic trope is wherever we find liquid water on Earth, we find life, whether we're under the seas in Antarctica, whether we're next to a nuclear reactor core, whether we're in weird, highly alkaline, highly acidic vents, anything. Liquid water equals life. But that kind of requires a few basic building blocks, things like carbon, phosphorus, etc. What does a life form have access to on one of these Hycean worlds?
Yeah. So for the definition of habitability, we haven't actually pushed it, like for the thermodynamic conditions, the temperature, pressure, and all that. Those we haven't pushed beyond what we see on Earth. In fact, the limits we have imposed are based on the limits that we know from extremophiles on Earth, like the maximum temperatures and pressures. So there is still some wiggle room there where you could push even further in temperatures, but we don't need to do that right now. But what is more important is the later part of your question, which is like what nutrients are available for the life forms. Now that's an important question, because for these sorts of planets, they don't have access to a land surface for the most part. Of course, if the oceans are shallow, for the definitions of these planets, we are giving a wide range of like how thick an ocean can be. So it is possible that the oceans will be shallow, and then you can still have access to the nutrients in some cases, like from the rocky surface underneath, and then you can have convection and mixing of the nutrients to the surface. But many of them may not have access to that, right? Because the ocean could be so deep that at the bottom of it, you would have basically high pressure ices or supercritical water. So then then they would basically cut off access from the nutrient pool underneath. Mm-hmm. And that is a problem for the conventional way of thinking about how nutrients are accessed by life on Earth. But the nutrients that you mentioned, the carbon, nitrogen, phosphorus, and so on, those are not the ones that I'm worried about, because those in a hydrogen-rich atmosphere almost come for free with the nebular gas. Right? When you accrete the nebular gas during formation, in addition to hydrogen, you also accrete molecules that contain carbon, nitrogen, all these volatile species, carbon, nitrogen, phosphorus, sulfur, and so on. So those could still be accessible. What is a problem is potentially the metals, which are usually sequestered deep in the core. And if you don't have access to the weathering of those that core to give back the nutrients, it could be a problem.
Yeah.
There are other ideas floating around, which is, you could get them from meteorites, for example, externally delivered to the ocean, and then that could replenish some of that. But then we could also think about, hypotheses on if life can evolve without those specific metals.
Yeah. So, I mean, this whole topic of how habitable really is an ocean world, and that's it's a whole other field of research that people are investigating. And I think with many of these fields, your first brush is like, well, it's a 100-kilometer thick ocean. Forget about it. There's no chance. And then someone at some point goes, well, wait a minute, what about this? And then everyone goes, oh yeah, okay, yeah, fine, it's better now, right? They solve it. So I think that's I think sort of, at first blush you sort of think, oh no, it's hopeless, and then later on people come up with really clever ideas. Like the Earth is accumulating 100 tons of space debris every year just from it falling through the atmosphere, and it would be raining down. And people have proposed like we could seed the oceans with iron to try to help minimize the impact of climate change. Well, maybe with a planet that is much larger, maybe it's got a multiplication of this stuff just raining down and falling in the ocean. Maybe the life forms have done a really good job of holding on to those precious elements as they for longer periods. So I want to sort of put this now we've sort of got all the building blocks, and I want to sort of put this idea into a larger context. Most planets are hydrogen worlds, are like in the universe. Like we haven't found them all, but based on the fact that most of the universe is hydrogen, it feels like a safe assumption. Most of the planets that we're finding are these larger planets. These somewhere between Earth and Neptune. Not now, maybe that's just we haven't expanded, we need better telescopes, better methods, etc. A wider habitable zone is better. Like it feels like you are delivering sort of a gigantic chunk of habitability to the universe with the research that you're doing. Is that what it feels like?
That's what we realized when we found this, is that it's got to be a sea change in our chances of finding life. But what I'm most excited about in all of this is that it's, I do a lot of theory. I do observational work as well. But this is mostly theoretical, with strong observational underpinnings. But what excites me most about this is that it's all observable.
Mm-hmm. Yes.
You can test it, right? So don't buy the theory. Wait 3-4 years. Let James Webb launch, and we even have approved observations on James Webb to look at some of these objects. So JWST will look at them.
Yeah.
And we have even found about 11 best targets that we have identified in this work. You can actually observe them, observe their atmospheres, determine if they have oceans, determine if they have any biosignatures on them. And if you found nothing, let's say in a dozen planets, that's great, right? We have just ruled out that those are not the conditions for life.
But
if we did that.
So I think that's really important, because we've talked so much about ice worlds. We've talked about Europa and Enceladus and maybe Pluto, and what about Eris, and you've got these worlds, Ganymede, you've got this thick ice covering with a liquid water ocean underneath, and maybe and a metallic solid core, rocky core. And I've heard estimates that there could be 1,000 times as many of those worlds as we have worlds like the Earth. The problem is they are impossible to study. Maybe
Yeah,
here in the solar system we can send a probe to Europa or Enceladus and be able to somehow drill under the ice. But if we discover icy worlds in another star system, we have no way to be able to analyze to see if there are biosignatures. But I think like the bonus, the special bonus that you're adding on the top of this is that you can analyze the atmosphere of these worlds and search for biosignatures in exactly the same way you'd be analyzing
yeah,
a terrestrial planet. And
yeah,
they're easier to look at because they're bigger. Potentially they're an easier target to analyze. They could very well be the first best place, like almost like we should stop looking at waiting to find those terrestrial planets and start analyzing the atmospheres of these worlds and testing out our techniques.
yeah. I mean, the reality is that there are already approved observations for other reasons. So for the same target, some of the same targets, James Webb is already slated to observe those planets because we generally want to understand the atmospheres of sub-Neptune planets because they're so important and unique. So we almost get, if there are biosignatures, if at all, or candidate biosignatures, you almost get those for free.
Yeah.
So in the first cycle of James Webb observation, some of them will be observed. So that is the important part in all of this. And to me, I mean, fundamentally, science is all about posing testable hypotheses and going and making observations to prove those hypotheses. Then they become established theoretical foundations of something bigger in the future. Whether if we detect, let's say we detect one of these biomarkers, potential biomarkers, whether they're actually indicative of life or not is also something we want to establish. You see what I mean? There could be false positives, this and that. So all that aside, the important thing is two things, as you pointed out. One is that these sorts of planets, have delivered an enormous catchment area, so to speak, like an enormous opportunity to search for life that both expands and accelerates the search for life.
Yeah.
And the second important bit is that it's actually doable in the next few years.
It's actually testable. Yeah. And so back to that idea of, I hadn't even triggered on that idea of the rogue planets. Like it's really starting to dawn on us now just how many of those rogue planets could be out there. At least as many as just regular planets, maybe. Maybe more. I've heard some estimates as high as like 10 times as many planets are actually rogue planets out there. And if they were ice worlds, there's no way to examine them for biosignatures. But now maybe there is a way. So
yeah, sorry, go on.
So, well, just go ahead first, and then I'll shift to my next.
No, I was saying like it is harder to detect the atmospheres of the rogue worlds.
Of course.
Having a star around which the planet orbits turns out is very useful for atmospheric spectroscopy of the planet itself. So that is the caveat. But you're right, is that in principle there could be a lot of rogue worlds as well.
But still, I mean, like a gigantic infrared observatory that's observing a rogue world that maybe is only a light year away from us, and detecting a Hycean world feels possible. Trying to analyze the geysers coming out of a moon around a rogue Jupiter feels tricky. Like it just feels next level difficult. And so I think these kinds of worlds provides just this first really useful step, some way to possibly analyze these things. But I think, as you say, just the standard analysis of these worlds, these kinds of observations would fall out as just part of the regular, like astronomers would absolutely be examining the spectra, seeing what they're seeing, and the results would come out of it. So we've painted this really rosy picture, and I want to bring the hammer down, which is like, you've got a planet that has a thick hydrogen atmosphere. It is filled with hydrocarbons. Life as we understand it here on Earth generates oxygen. The higher life forms enjoy to breathe that oxygen. You add oxygen to one of your Hycean worlds, and we've got a problem.
You got a big problem there.
Yeah.
It turns out life, and most life on Earth, or like that, the life that we are talking about that you just mentioned, breathes oxygen, but there is life on Earth which also survives in very high hydrogen concentrations. There have been studies which showed that you could have 80% hydrogen and life survives just fine. And even laboratory experiments have showed that even in 100% oxygen, life, some microbes survive just fine. So oxygen, yes, most life might need it, but not like all life.
Right. But I think, like, obviously, we have a completely separate ecosystem here on Earth down to the bottom of the oceans. You have the life that is huddled around these black smokers, and all surface life could disappear tomorrow, and there would still be life on Earth because they don't require the sun. You could destroy the sun, and they would be fine with that.
Yeah.
So I can imagine some version of that, but I think in our minds, when we imagine an ocean world, we imagine these giant krakens and space whales and creatures flying around in the thick hydrogen atmosphere chasing little hydrogen birds. All that kind of goes out the window, doesn't it? You've just got a lot of bacteria fighting for the rare piece of iron that happens to fall from space. Yeah,
I mean, we have to be very notions of life in these sorts of studies. Because it's very easy to go off the tangent and say, we'll find all kinds of oceanic life. And that I don't think is the case. We have to be very cautious and conservative and say we'd be lucky if we found microbes, like extremophile microbes on these planets. And we'd be lucky if they gave the signatures that we think such microbes give out. And then we'd be lucky if we actually detected them. So there are many chains of argument before we can establish. And even if we find a molecule, we have to be really sure that is a biosignature. So I don't think we should, get ahead of ourselves and claim of complex life forms. But any life detected is a major breakthrough, isn't it? It's like a sea change.
Maybe the first time, sure, fine. We discover life on another world for the first time, fine. It's like the most important scientific discovery in the history of humanity, fine. But what else you got, right? Like now I want space whales.
Yeah, exactly. So the thing is, that is why I have had arguments that maybe we should focus exclusively on these sorts of planets. My response is, in the short term, yes, because that's the most accessible and that's our first bet. But we want to make sure we keep the search on for terrestrial, like the regular the terrestrial habitable zone concept and terrestrial planets, terrestrial size exoplanets with the right conditions that we know of as on Earth, and continue looking for those as well, because ultimately that is our eventual goal, to find an Earth twin that is the holy grail of exoplanet science. So we don't want to stop here, obviously, but this is a big stepping stone in that direction. Because if you just bank on trying to find that, it's like a more than 10-year venture.
Yeah, we're at the point now where astronomers are and exobiologists are trying to figure out what are the biosignatures that we should be looking for in the atmospheres of other worlds. What are the gases that if you detect them in your spectroscopy, you've got a very clear indication of that there's life there. And I mean, we've seen with the big argument over phosphine on Venus, like Venus is it's right over there, and people can't agree that these signals were detected. Mars is just over there, And again, people can't be sure if the sources of methane indicate life or indicate volcanic activity.
Yeah.
Do the simplified ingredients of a Haitian world allow you to find weirder outliers that could be a more strong indication of a biosignature?
Yeah, so there are many aspects there. They have just a much wider range of possibilities. Both in terms of Venus and Mars, the temperatures, are not like Earth-like temperatures. You see what I mean? So we are trying to, in case of phosphine, there are arguments on it. Does phosphine really indicate the existence of life, or there can be false positives and all that. For Haitian worlds, it's a different set of problems in the sense that the regular biomarkers, let's say methane, you wouldn't expect that to be a robust biosignature on a Haitian world. So, like in our paper, what we showed that what is our best bet is to focus on what are known as these secondary biomarkers that are not produced in massive quantities, because those can have false positives like methane. But these secondary biomarkers like methyl chloride or dimethyl sulfide, these things which we know are produced by organisms on Earth, but in very small quantities. We are talking about a part per million. But those are possible on these planets because the temperature and pressure conditions are right for such organisms.
Yeah.
And those can be easily detectable as well because their atmospheres are so puffy that with JWST they're easily detectable.
Yeah.
At least for the nearest systems.
So, and do you think that then these observations under maybe more tighter constraints will help to inform as you extend out to other kinds of worlds?
Yeah, so there were, even for Earth-like planets, there were previous studies arguing that maybe we should focus more on the secondary biomarkers than the primary ones, like oxygen and methane, even for Earth-like planets. So what we are saying here is that those exact biomarkers are even easier to detect on Haitian worlds. So, and they provide lots of opportunities, which makes them very favorable.
Yeah. It sounds like if they're out there, it sounds like a real gift. Is there any way to get a hybrid? Like, is there any way to blur the line between a Haitian world and a terrestrial world?
Yeah. So for small planets, so far what I've only talked about the upper limit of radius, but there is also a lower limit where we're saying we are prescribing a minimum amount of water, 10% by mass. Turns out even that amount of water is a lot compared to what we have on Earth, right? On Earth, it's less than 0.1%. So that is where you start to blur the lines, is that if you just had a mass and radius measurement, that size planet can also be explained by, an Earth-like planet with less amount of iron, like a silicate-rich planet, and a little bit less hydrogen. There are a combination of species, compositions can explain that. So that's where you blur the lines, and then you need an atmospheric observation to establish whether it's actually, has the requirements that we prescribe.
So how many of these do you think are out there?
It's hard to say because the statistics are not clear yet. But there could be a lot because we have already identified close to a dozen around very nearby stars. By nearby, we are talking about tens of light years to around 100 plus light years. So my guess is that there could be a lot of them out there.
But the universe is a big place, so there's a lot of everything.
No, even in the solar neighborhood, there could be a lot of them. So that is the problem.
Even the solar neighborhood is a big place, so there's a lot of everything.
Exactly.
But because I think at this point, astronomers are starting to think that there could be one Earth-sized world per star. Like
Earth-sized, not
right, of course, not in the
now.
habitable zone, but size. But you've taken this idea of a habitable zone, you've just thrown it out the window, and you said it's all good. So like, does every star system have a Haitian world? Do half of star systems 1/10, 1/1000th?
I wouldn't hazard a guess at this point. We just established this this
This is a
category.
safe place. You can hazard a guess, and
No, it is not.
nobody will
No,
listen to this. Don't worry about it.
no, it's not about that. It's that someone has to do the demographic calculations, and I would think there would be a lot of them. But the problem here is that it's not just about mass and radius. If you said radius and mass limits within the Hycean limits, then I would say tons. Tons, at least one per star or something like that.
There we go.
But that is not enough for a Hycean world. You also need the right temperature around the right star.
Right.
And that changes with stars. So all this combination of metrics means that you actually have to do a calculation to establish the demographics. So, but it's more than Earth-like habitable planets. That much I will say. It will be significantly more than Earth-like habitable planets.
And so that goes back to this idea that this is a great place to start. Let's find these worlds. Let's analyze their atmospheres. They're easier to look at. There's probably more of them out there for us to find. So we'll probably find ones that are better positioned for say James Webb or Ariel or HabEx. These to be able to analyze them and get some really good information. Use that as a way of learning to look at worlds that we have because there's only going to be so many places we can point James Webb at and get some work done. So I think it's sort of a really interesting, the ramifications of this sound really fascinating, kind of as interesting to me as the discovery of geysers on Enceladus and Europa, that suddenly this whole new class of worlds has come into focus, but then kind of makes the question of like, where is everybody even more complicated, because now suddenly there's more worlds that could be habitable. Right. Eventually, just space itself will be habitable. So what comes next?
So we have JWST observations lined up, both by our team and by other teams for like at least a couple. Like we are observing one such planet, K218b, and there are other planets that are in the JWST Cycle 1 program. So we'll see what lays in store.
What would be, I guess, you've got time on James Webb. What would be an observation that you could make that would feel really impactful?
So in our paper, actually, we demonstrated that at least a couple of these biosignatures, potential biosignatures we are suggesting, can be detected with already approved time on JWST. So if you make that detection, that will be great. But even without it, if we make detections of water, ammonia, methane, HCN, and things like that, that would at least give us some constraints on the possible presence of an ocean, and atmospheric conditions and so on. So, regardless, in the next few years, assuming all goes to plan with JWST, we'll learn a lot about such worlds, independent of their habitable potential. And that is the exciting part to begin with.
Yeah, it's really interesting. And so now all we need is James Webb to launch.
Absolutely.
It's going to happen any day now. Nikku, thank you so much for taking the time to chat with me today. Really exciting concept discovery, and I think it really feels to me like this is going to have very big implications, assuming the math holds. It's going to have very big implications for the search for life. It in reading it really felt like one of those influential papers that is going to have ripples down the road as we learn more and more about the universe. So thank you so much for
thanks for having me. And I would like to especially thank the exoplanet community, actually, because we as a field have found thousands of planets, and we wouldn't be here talking about this if not for missions like TESS and Kepler and various other observation facilities that have discovered these worlds. And and it's looking really promising the decade ahead. So I thank all my exoplanet friends and colleagues, and thank you for having me here for this great discussion.
If people want to follow your work and see what you're up to, where should they go? What's the best place where people can see what you're up to?
So I post all my papers on my website, so you can just Google for me and you'll find me. That's the go-to place.
Terrific, wonderful. Well, again, thank you so much for the interview, and if you do. Once you had those observations, please come back and tell me what you found.
Will do.
All right.
Thanks
Thank
for
you so
having
much.
me. Great
All right.
chatting.
Bye-bye.
Thanks. Bye.